Hey, we've been looking at two different types of problems involving gravitational potential energy. One was reeling in a rope or chain that was hanging, something like this, and then also pumping liquid out of a tank. And I wanted to take a minute to point out that those are really the same problem. And I want us to, analyze them the same, really. One just has less dimensions than the other. So the reason calculus is needed in both cases is that we're adding gravitational potential energy by lifting something up higher. It's now up higher, it's got more potential to move by falling back down. And the problem is each little piece of this rope is getting displaced a different distance. All the rope's going to end up here, but it all starts at different places, so that displacement's different for every little piece of that rope. Same thing with the water in this tank. It's all, let's say we're going to displace it up to the top of the tank. I want to make these kind of really analogous. So we're going to reel all this rope up to here. We're going to pump all that liquid up to the top. And same thing, all this liquid's going to end up at one height, but it all started at different heights. So each little speck of liquid in here that exists at a different height is getting displaced a different amount. Okay, so in both cases, we want to think about what it is we're doing at the essence of approximating it. And what we want to do is get a slice of our object that's all roughly at the same height, because then we can say that it's all roughly being displaced the same amount. So we partition our interval here, and we look at an arbitrary piece here. So say this is my kth subinterval, and say we're looking at some y sub k in that subinterval. Okay, so on the rope, that translates into a piece of this rope, like this. And on the tank, that translates into a cross-sectional slice. If I'm using y sub k there, it looks something like my little bit of length or my little bit of volume. Okay, so now, what do we want to know? Work is a force times the displacement. And for gravitational potential, the force is weight, because it's the force of gravity. So, in both of these cases, I need to know how much this little piece weighs. That's our force. So, over here, the weight of that slice, just the one little slice, I'll call F sub k because it's a force. Well, how much does that little piece weigh? Well, it has some weight density. And because it's a one-dimensional problem, it's just that weight density times that length. And then over here, since this is a little cross-sectional slice, our weight would be our weight density times our volume of that slice. Well, I made these have the same weight density. This is one-dimensional, so it's pound per foot. So 62.4 pounds per foot. And how long is this little piece? It's delta y sub k. Over here, 62.4. And now we need a little more information because we need that volume, pi r squared h. So we know the height of that cylinder, it's delta y sub k, but we would need the radius. So this guy really needs a two-dimensional coordinate system to keep track of things. So let's say that this radius up here is, I don't know, 4 feet. So it's the same height as the rope, 10 feet over 4. So we can think of this as a volume of revolution, and the equation of this line is y equal, it goes up 10 over 4. All right. But the radius of this slice, you know, at this y sub k here, the radius is actually that x value. So what is x in terms of y? X is 4/10 y, or 2/5 y. So in our weight here, 62.4 pi, radius is 2/5 y sub k squared, and the height of that cylinder is delta y sub k. So a little slice of this and a little slice of this, find out how much it weighs, find out how much it weighs. The other part of work is how far is it going to get displaced. Well, in both cases, we're assuming that we're at some y sub k and we're going up to 10. So that displacement, bigger minus smaller, it's one of the reasons I like my coordinate systems bigger going up, because when I'm trying to measure a distance, I just naturally think of the top minus the bottom. If I had this coordinate system flipped upside down, that would not be the case. So, okay, so we know how much this little piece weighs. We know how much it's going to get moved. So we know the work on that little piece. The work being done on that little piece is the force, 62.4 delta y sub k, times the displacement, 10 minus y sub k. Over here, the work is the force, 62.4 pi 2/5 y sub k squared, delta y sub k, times our displacement, again, 10 minus y sub k. And then our integral, in both cases, you think about the chopping. We chopped this rope from 0 up to 10. We chopped this water from 0 up to 10. So what got chopped? We'd be integrating from 0 to 10. This thing, and I guess over here I'll just write it. Finish this off. 0 to 10, 62.4 times 10 minus y dy. Over here, 62.4 pi, what is that, 4/25 y squared, 10 minus y dy. And this is a work, it's a force times a displacement. Force was in pounds. Displacements were in feet. So in both cases, this answer is going to be some amount of foot-pounds. So dimensionally, they're not the same thing. This thing is this slice is 3-dimensional, this slice is 1-dimensional, but at their essence, what you're doing is the same. You're figuring out how much that little piece weighs and how far it's being lifted. And you're taking the product of that to find out roughly what the work is on that. And then these approximations become exact when we add them all up and let the deltas shrink down. So think about, in these cases, writing your diagram. Based on some of the questions I've been getting, it's clear people are not thinking about the geometry of what's happening. They're just trying to kind of take some numbers that are given to them and throw them into an integral. I'm much more interested in all of this stuff. Can you analyze what's going on? Get the quantities, understand what it is you're assembling there in that integral, instead of just slapping together that integral. So I hope that helps. I hope that parallel, you can see these are really the same thing. This is just kind of a simpler 1D case of the pumping problem, which is 3D.